The second broad class of methods for finding roots of one-dimensional equations are known as open methods. So if we have no idea where the root of a function might be, one possibility, in fact really almost the only possibility, is to use open methods. Open methods also have the advantage that usually they converge more rapidly than bracketed methods. Not always the case, but it's often the case. There is a downside to that, and that is that also sometimes open methods can diverge. So you have to be aware of that when you're using them. In Engineering 1060, you learnt three different methods: the Newton-Raphson method, the secant method, and the modified secant method. I am going to very briefly review those three methods here, but algorithmically these methods are identical. In other words, the process that you're using is the same for all of them, and in actual fact there's only one formula that you change. So what we're going to do to begin with is we're going to go through the concept, and then we'll go into the details of each of the different methods. So the basic concept of the open methods are as follows. We have a function represented by that blue curve there. We need to start with a guess, and I'm going to call the guess xi. It's the current guess. The next thing we need to do is we need to calculate the function value at xi, that's that green point there, and we also need to know the slope of the function there. I'm not going to say yet how we calculate the slope, that's where the three different methods come in, but just keep in the back of your mind that we need the function value and the slope. So I'm going to call the slope mi, just so that we don't get it confused with anything else. But what mi is actually equal to, it's equal to df dx evaluated at the point xi. Okay, so if we know that slope, we know the function, we've got everything we need. So we calculate those things. We then calculate the new point using the following function. Xi plus 1, that's our new guess for the root, is equal to xi minus the function value f of xi divided by the slope at mi. I think it's a good idea to remember that formula, but even more important, you should know how to calculate this formula, and it's based on this right angle triangle here. It's a very simple formula to derive, and you should be able to derive it. I'm not going to do it here though. We then go and say, well, is our function value at xi plus 1, is it close enough to 0? If it is, then we've found the root. If it's not, then we need to repeat steps 1 through 3. We calculate the slope at this point, at xi plus 1. We calculate the tangent, or the tangent curve, to see where that crosses. And then our next guess, xi plus 2, is our next guess for the root. Okay, and we calculate the function value there. Is it close enough? If it's not, we need to go through the process again. As with bracketed methods, we need to decide when is or what is close enough, and as before, we look at, is the absolute value of the function at our new guess, xi plus 1, is it less than the precision that we've prepared to accept, where precision here is what I've previously been calling epsilon. Okay, so that's the basic underlying idea. So now let's quickly go through and look at the three different techniques. The first is Newton-Raphson. It's the most common one, it works very well, and you can use Newton-Raphson if you have an analytic expression for the derivative f dashed. So if you know, for example, if our function f of x is equal to sine x, then obviously f dashed of x is equal to cos x. And we have an analytic expression that we can use in the Newton-Raphson formula. So if we have that, we can use it for the slope mi. So our generic formula, which is this formula here, we replace mi by the analytic expression for f dashed, and we come up with the Newton-Raphson formula as xi plus 1 is equal to xi minus the function value at xi divided by the slope of the function at xi. That is the Newton-Raphson method. We've all used that one before. An alternative to the Newton-Raphson method is the secant method. So sometimes we don't have an analytic expression for the derivative, so we don't know what mi is equal to. However, usually we can imagine that we've got 2 points, our current guess xi and our previous guess That's xi minus 1. And we can calculate the function values at these 2 points. So f of xi minus 1. And approximate the derivative as the slope of the line that passes through these 2 points. It's only an approximation, but as these points get closer together, it will become a better and better approximation. Now, it's very easy to show that the slope generated by this method is given by, approximately, the difference in the function values, f of xi minus f of xi minus 1, divided by the differences in x values, xi minus xi minus 1. That's just the rise over the run, and it's based on this triangle here. Okay, so you can easily calculate that the slope is approximately equal to that thing there. The only tricky thing about the secant method is when you start off the method, you don't have the previous guess. So you actually need to start with 2 values the very first time you go into the secant method. You need to choose 2 points. The nice thing about the secant method, however, is these 2 points do not need to bracket the root. So this is our approximate slope formula here. We replace that in our generic formula, and this gives the secant method formula that looks like this. Again, I don't expect you to remember this. This formula will be on the formula sheet in an exam if you should need it. However, you should know how to derive this. Another interesting point that is worth noting is that this formula here might not look like it, but it is exactly the same, well, it's exactly the same formula as the formula for the method of false position. It's written in a slightly different way, but the formulas are exactly equivalent. The only difference between the secant method and the method of false position is that in the method of false position you have to always be bracketing the root. In the secant method you do not need to bracket the root with your 2 points. You can use any 2 points. The final variation is what's known as the modified secant method, and a little bit like Newton-Raphson, you only need 1 point to start the modified secant method. So again, you calculate the function value, f of xi at our guess, xi. We then choose a small increment. Let's call that small increment delta, and we calculate the function value of f of xi plus delta. So that's that green point there. Just like in the secant method, we approximate the derivative as the slope of the line that passes through those 2 points. And so where that line passes the x-axis, that's our new guess. And so the slope of this line here is given by that expression there, f of xi plus delta minus f of xi divided by delta. Now the astute of you will look at this and say, well, the limit as delta goes to 0 of f of xi plus delta minus f of xi divided by delta, that's equal to the definition of the first derivative. And indeed it is. So if you choose delta smaller and smaller and smaller, you're getting closer and closer to the analytic result. In other words, you're getting closer and closer to the Newton-Raphson method. So we just need to replace mi by our modified secant formula in our generic formula here, and it gives us the modified secant method. Again, I don't expect you to remember this formula, but I do expect you to be able to derive it. So those are the 3 basic open methods. There's a key idea behind all of this, and the key idea is we estimate the slope of the function and find the tangent crossing point using this formula here. And the 3 methods that we've looked at are just different ways of calculating this slope. Okay, I said previously that although open methods converge more rapidly, generally speaking, there are also some problems. And there are things that can crop up, for example, what are known as limit cycles. So if we start off for a guess, for example, we draw the tangent, we get a new guess, we come down, we draw the tangent. And there are cases where you can go around this loop and eventually this loop closes in on itself and it never changes. It never gets to the root, but it just sits on this what's called a limit cycle. There are also other cases where this thing can diverge. In other words, it can go out further and further to infinity. There are other situations where you might get poor convergence. You may eventually get there, but an example is this function here where we choose an initial guess at x0, And if we just follow this round, we can see that the route doesn't seem to be converging very nicely at all. It's going all over the place. The final problem that can arise is if we happen to choose a point where the slope is 0, we're going to go off to infinity. So these are some of the problems we can get with open route finding methods, and you need to be aware of this, and sometimes in your code put in checks to make sure that you're not getting problems as a consequence.